Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the University of Wisconsin-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to welcome back to Wednesday Night at the Lab, Eric Carson. He's a geologist with the Wisconsin Geological and Natural History Survey, which is also part of the Division of Extension here at UW-Madison. Eric was born in Madison, the one in Indiana. And he then went to high school at Morgantown, West Virginia. He stayed in Morgantown to go to West Virginia University, where he studied geology for his undergraduate degree. Then he came to UW-Madison to get his master's in geology and stayed to get his PhD in both geology and geography. Tonight, he's going to speak with us about investigating glacial Lake Yahara. I had no idea that the four lakes once were one. I'm looking forward to hearing how that all happened. Would you please join me in welcoming Eric Carson back to Wednesday Night at the Lab.
And not just back, but this makes me a 3-time offender here, so maybe you'll kick me out for good one of these days. Yeah, so I'd like to talk to you about some of the research that I've been doing, one of the research projects of many that I have going on, which is why I keep coming back here to talk to you all. I appreciate you all coming out on what might be the last nice evening of the autumn here, so let's get into it. I would like to start by mentioning that this is not my work alone. So Libby Ives has worked on this. She was a graduate student at UW-Milwaukee, and she's at JPL out on the West Coast now. And Casey Stolzman and Elmo Rawling from the Wisconsin Geological Survey have also been participating in this. So when I say I did things, it was mostly them doing things and me thinking about them. All right, so let's start by looking at Wisconsin. This is sort of the how it's going now, and we can go back to how it started 20,000 years ago, and we'll have something like this. So this will be the peak of the last glaciation, what colloquially is known as the Wisconsin glaciation. This is ice flowing out of the Hudson Bay lowland primarily, flowing down to the southwest into Wisconsin. There are lobes that covered the northern part of the state, and then lobes of ice, these sort of semi-autonomous, semi-connected margins of the glacier coming down into the eastern parts of the state, so the aptly named Green Bay lobe and the aptly named Lake Michigan lobe. So ice of the Green Bay lobe of the Laurentide ice sheet is what was flowing down right here into Madison, flowing down just a few kilometers to the west and south of us, for the absolute margin of it about 20,000 years ago. I'll take a moment and talk about the area off to the west of it. So this is the driftless area. This is the area that much of my research has been focused on. I've got a background in training to work in the driftless area, and it's been instrumental for this work that I'll be talking about today. So let's look at that. I would expect that many of you are familiar with it. So it's the topography of the state, we like to say. It's the portion that was never glaciated, not just during the last cycle of glaciations, but any of the cycles of glaciations that have occurred over the last 2.5 million years. So what we see is, rather than a landscape made up of glacial sediments and glacial landforms, we see a landscape dominated by rivers carving down into the bedrock. So you can see that sort of dendritic branch-like pattern of rivers and their valleys stretched across the driftless area. Now, I will take a moment for shameless self-promotion here and mention that just earlier this summer, our office published a new report on the driftless area. So this is what we consider to be the definitive paper on the extent of the driftless area. If you look online, everybody's got their own definition for what the driftless area is and how big it is. And Minnesota likes to think they're part of the driftless area, and Iowa likes to think they're part of the driftless area. But the simple truth is they're not, at least if you're defining it by the glacial geology. So in this publication, it's not just myself, it's authors from the Minnesota, the Iowa, and the Illinois State Geological Surveys. So the four of our surveys have combined to publish this paper. We all agree on it. It is, as far as we're concerned, the definitive answer to what the driftless area is, if you're curious about that. So there is the tiny URL down there at the bottom, or you can go to the Wisconsin Geological and Natural History Survey's website and find it pretty easily. Okay, with that being dispensed, let's talk about that topography of the driftless area, those rivers that are carved down into the bedrock. It doesn't just exist in the driftless area. It does exist across large portions of Iowa and Minnesota, and even into southeastern Wisconsin. So we see this map here. This was a map published in the 1970s that is a depth to bedrock map. So the reason that the driftless area doesn't show up anymore on this map is all of the bedrock is right close to the surface. And so there's no depth to bedrock in any real sense, except for along the lower Wisconsin Riverway. If you get farther east into the southeastern part of the state, there you've got this same bedrock that's carved by these rivers, but now it's buried by tens or in many places hundreds of feet of glacial sediment. And so here it pops up in these bright oranges and bright reds to show us that the same kind of river valleys exist in the other parts of the state. They're just covered by glacial sediment. And as we look at that, it's probably too hard to read any of the place names or anything on that image. But we can highlight this area right here. This is the Madison area. And the bright red line you're seeing through there, that is a deep bedrock valley. That is the ancestral Yahara River Valley. The Yahara River carved this deep valley right in this area prior to the cycles of glaciations. So it's no accident that the four lakes of Madison are lined up in a nice row from northwest to southeast. They're all hiding down in the remnants of this river valley that's now buried by a couple hundred feet of glacial sediment. If we go back to this though, if we go back to where that topography is exposed at the surface in the driftless area, this has been really key to this research that I've been doing. I've talked about this, it was over a decade ago here at Wednesday night at the lab. Some of my earliest work using the topography of the driftless area to constrain the timing of the last glaciation. And the way that works is based off this very topography that we get in the driftless area. As it turns out, dating when glaciations happen, when the ice advanced and when it retreated, tends to be very difficult. And a lot of that has to do with the fact that glaciers are sort of wet, sloppy margins, wet, sloppy places. In a lot of ways, it's just procedurally, process-wise, difficult to date the events. But what we have here is this nice landscape with great drainage of the lower Wisconsin Riverway to funnel water away from the margin, but also plenty of little nooks and crannies where little lakes can form. And I'll talk about a bunch of little lakes during the course of this talk. And just like Glacial Lake Yahara, none of these lakes exist anymore. They formed back during the time of the glaciers. They drained back during or just after the time of the glaciers. And what we found is, while it's really hard to date the glacial events, we can understand what glacial events caused these lakes to form and to drain. And so if we can date the lakes, then we can take those dates and say, aha, this glacial event made that lake form or drain. So in that way, we can actually use these things to get right at the actual timing of the advance and retreat of glaciers, even though we're not in the glaciated part of the state. So we'll flip over to a different view of this. So this is just a grayscale view of the same sort of area. You can see the dark gray of the lower Wisconsin River Valley. You can see the lakes of Madison down in the southeast portion of the lake. You can see the Baraboo Hills, and then you can also see that blue line that squiggles across the central portion of the map. That is the limit of the last cycle of glaciation. So if you're on the east side of that, you're in the glaciated part of the state. If you're on the west side of that, you're in the driftless area. That, topographically, we refer to it as the Johnstown Moraine. So that's the ridge of sediment that was deposited by the glacier at that maximum position. And over the course of years, I have been looking at many of these lakes that existed just off beyond that margin. So all of these are related to this work. These three up here, these are actually part of the Great Glacial Lake Wisconsin system that covered the central portion of the state. So I've even included it up here. But we have all these rivers in the Devil's Lake area. down on Black Earth Creek, down along the lower Wisconsin River. So we've got plenty of these lakes that are in here. And what we're interested in from these for this work is chronology. We're interested in timing of when they formed. And so what we need to get at that is the sediments from the lakes. And so we go about that with coring. So I have been a huge proponent over the years of sediment coring at the survey, and I've been a pioneer of sorts at the survey of using a specific type of coring, and that's what's shown here in the image. It's a method of coring called geoprobe coring, and it takes a steel rod with an interior diameter of about 2 inches, and we put a polycarbonate plastic liner up in it and hydraulically hammer it down into the ground. And I like to be a good scientist and use the metric, but these guys go 5 feet at a time. So when I talk about a lot of the geoprobe coring, I have to talk about English units of measurement because it doesn't work to go in multiples of 152 centimeters. So we'll go in feet. So they hammer down 5 feet, pull the tube back, we take the polycarbonate liner out, and we have our 5 feet of sediment. And then we put a new liner in, go back down, and keep going. And in a lot of places, we can go down 50, 60, 70 feet and get pretty reliable sediment recovery. For our purposes, it's also fast. We can get a core like that probably within an hour and a half. It's inexpensive in the terms of these things. So the contractor we work with, it costs us about $10 per linear foot all in to collect the core. For our poor bedrock geologists, they're talking more in the range of $125 to $140 a linear foot these days for their coring. So I can do a lot of this geoprobe coring, and over the years I've done literally hundreds of these cores for various geologic research and mapping projects that I've done in the state. Here's an example of us taking a core. This is at Wilkie's Gorge, just west of town. And once we collect these, we take them back to our lab. We will wind up with cores that we can split at our sediment laboratory. We can photograph them, describe them, take whatever samples we want from them. And one of the things that we have found over the course of our research is that these little glacial lakes, even though they were in existence during the peak of the glacial cycles, and even though many of them were within just a few kilometers of the ice margin, plenty of them are loaded with plant macrofossils, the perfect kind of thing for radiocarbon dating, which is the most accurate, most precise dating methodology that we have in our toolkit. And so we have the ability to collect lots of cores, collect them quickly, collect them inexpensively, and they're typically abundant with plant macrofossils. So here's just an example from one of our cores. You can see a nice snail shell in there, a gastropod shell. Just to the right of the gastropod shell, this sort of chewed up looking area, that's matted plant fragments, leaves. So plenty of material in these cores for us to date. So we go with all this coring. We've collected these from numerous places. We've understood the processes that cause these lakes to form and drain. And so I'm going to shrink this down, and I'm going to give you a moment of some of the data from sort of our accumulated coring expeditions. So this is a diagram that on the vertical axis has age, so that's in thousands of years before present, going from 17,000 down to 25,000 years before present. And on the horizontal axis are different locations that we've been collecting these cores. So these are all from different publications of ours. Now we're not going to go through this in detail. That's not the point of it. The point of it is this part off on the right where it says 1, 2, 3, 4. That's saying that in the paper, in the published paper, it's describing the glacial events that are constrained by these lake dates. So this bottom one down here, this was where we were able to constrain the end of the advance of the Green Bay lobe, which happened 24,600 years ago. We were able to constrain some of the dynamics that went on with it, able to constrain when it started to retreat, which would have been right around 18,500 years ago from the Baraboo Hills area. And we were actually able to constrain when the ice retreated as far back as the eastern end of the Baraboo Hills. And when that happened, there was a catastrophic drainage of Glacial Lake, Wisconsin, and that's what formed the Wisconsin Dells in about a week's worth of time. And that happened 17,400 years ago. So we've elucidated all of that from our lake cores. But if you look back at the map, what do we see? We see that everything is off in the driftless area. Everything is relating to that maximum ice time. And so the question that we're going to get at this evening is, what about events after the onset of retreat? What about lakes that existed behind the margin, that were exposed, that the ground was exposed and the lakes formed as the ice retreated back? So that's going to encompass right here where we are in the glaciated part of the state. So let's flip to a little bit different view. You know, again, this should be fairly familiar. We've got the Wisconsin River Valley up here in the northwest corner of the map. Dane and Jefferson counties highlighted. The four lakes of Madison tucked in there. So we'll be looking at this area for the rest of our talk. And if we add on some of the features that we had previously, so this is the Johnstown Moraine cutting across the map. So that's the maximum position. That's the moraine, the ridge of sediment that was formed when ice was at its maximum. But as the ice begins to retreat back, it doesn't do it monotonically. It does it in fits and starts. It'll retreat and sometimes it'll pause, or it'll retreat and sometimes it'll advance a little bit. And each time it does that, it leaves another set of moraines, another set of ridges that show us where the ice was stationary at. So in this area, we don't just have the Johnstown moraine that marks the maximum position. We also have recessional moraines, we call them, moraines that were formed as the ice was retreating. So just off to the south of the Four Lakes of Madison, we have the Milton Moraine. And then a little bit farther back in northeastern Dane County and across Jefferson County, we have the Lake Mills moraines. So we have these different features in here. We have places on this landscape that lakes could form. We have glacial sediment, but we also have that old, deep carved bedrock system underneath it, so plenty of places for lakes to form. Now, if we look at some of the work that our office has done before, this is a publication by one of our geologists from decades back, Lee Clayton. So this is a publication that he had out from some of his mapping work, and he was looking at some of the glacial lakes that existed in this area as the ice was retreating and after it had retreated. So there's 3 of them in here of radically different sizes, and we'll point all 3 of them out because they've got different things to say about the events going on. So one of them is Glacial Lake Middleton. We're not going to say a whole lot about Lake Middleton. If you're familiar with the local geography where the Middleton Airport is, that's the bed of Glacial Lake Middleton. At the Milton phase, the first recessional phase, the lake existed right in front of the ice, and it actually drained down Black Earth Creek. And then as ice retreated farther back, Glacial Lake Middleton drained and formed the gorge at Pheasant Branch. Thank you very much. So it formed that little gorge as the water drained back towards the ice, back towards what today is Lake Mendota. Then across Dane County, we've got Glacial Lake Yahara, so we can see the footprint of the 4 lakes in there, and then the footprint of Glacial Lake Yahara. You can see that it's not a whole lot more expansive. It covers the area more extensively, but the maximum extent of it isn't all that much greater, and that's because the whole thing is still contained within the ancient Yahara River Valley. And then off here to the east, covering much of Jefferson and into Dodge County, is this Glacial Lake Scuppernong. And this was Lee Clayton's envisionment of the lake at the time. He envisioned it with these drumlins, these glacial landforms sprinkled in here, almost like a Spanish armada of islands across this huge expansive lake. The reason we've got both of these on here, and the reason I'll be talking about Glacial Lake Scuppernong, is that those 2 lakes, Lake Yahara and Lake Scuppernong, were connected down here in the south, and they both drain down through the Rock River. And so the history of the 2 of them is intertwined, and we've had contemporaneous work going on these days looking at those 2 lake deposits. So I'm mostly going to be talking about Glacial Lake Yahara, but I'll fold in a little bit of the work of Glacial Lake Scuppernong as well. So let's zoom in again on the Madison area. We've got the grayscale, we've got the 4 lakes that we have today, and the Glacial Lake Yahara extent, I'm not even going to bother putting it on here. it's very difficult for us to see it, to find it on the landscape today. There simply aren't a lot of features, beach deposits and the like, that we'd normally look for. Generally speaking, anything in the darker grays on this map would have been of Glacial Lake Yahara. What we were looking for were the parts that were closest to modern lake level. And there's a reason for that. You know, through all of these areas up here that are the dark grays but a little bit higher, those would have been covered by the lake, but the lake itself would have been shallow and there wouldn't have been very much space for sediment to accumulate. So what we were looking for were places where it was closest to the center of the old valley, so it was deepest and there was the most space for sediment to collect, and also the places that were closest to modern lake level. So they were sort of the last places that got exposed above water level as the lake fell. And so by that way, we can actually get at when the lake ended if we go to those lowest spots. And hopefully, with those lowest spots, that also lets us get at when the lake formed, if we can find some datable radiocarbon material from way down deep in these valleys. So here in the blue dashes, these are the areas that we were isolating. These are the areas that we were looking at. So some of these you'll recognize. There's the Pheasant Branch Conservancy. That's Cherokee Marsh up there. This is the Door Creek Marsh and Conservancy. So kind of nice, wet, sloppy places we're talking. Turns out all of these were within a meter or so of modern lake levels. What that meant from a logistics standpoint for us is that much of this work had to be done during the winters, when these marshes were frozen over and we could get out on them to core. Sure enough, though, we did find plenty of good spots. We found 9 locations within the Glacial Lake Yahara Basin that we were both able to be confident that they hit the criteria that we were looking for, and also that we had access to them. Either in a few places there were roads that cut across the marshes, and we were able to core right on the shoulders of the roads. But there were also quite a few of these that the management organizations that are in charge of them were gracious enough to give us permission to get our drill rig out onto it when the marshes were frozen. You know, with the way science works, that actually held us up for a year. We wound up doing most of the coring for this in the winter of 2019 going into 2020. We wanted to do it the year earlier, but the marshes never got frozen enough for me to be confident that I could run that drill rig out and get it back, because the last thing I'd want to do is leave that out there for a summer or more. So we'll start by showing sort of the closest to here that we can. So this is right at University Bay. This is one of the spots that hit the criteria. It was also easy access. There's the athletic fields right there. There's the marsh. We did this during the winter, but we didn't really have to. Here's a zoom in on it. You can see there's the modern marsh right in here, the athletic fields here off to the west, and the UW Hospital complex right down here. And then you can see Picnic Point off here on the north side. So here we are out with our core rig. This is that geoprobe core. So this is what we use for all of these, especially in the marsh. It probably weighs a couple tons, which is why we wanted to have some good frost in the ground. This unit is on self-propelled tank track, so once we're confident that the ground is frozen, we can take it wherever we want to go. Just to give you a couple more photos, because we like to do geology out in the field rather than in a lab or in an auditorium. So here we are. This is on the east side of Lake Giganza, a spot where there was a road cutting across the swamp right near Vitruvian Farms, if any of you get your CSA from there. This is down on Door Creek on the north side of, I'm sorry, the last one was on the east side of Lake Wabisa. This is on the north side of Lake Giganza. So this is us going out on a nice snowy day, pushing through the snow with the rig, letting it cut a path for us. And then this last one's going to be in Pheasant Branch. So this was another bright sunny day where we were able to go out and collect these cores during that winter. In fact, when I was looking at these photos earlier today, I was taken aback a little bit because one or two of these that I showed you was collected on February 24th of 2020. So just a few weeks before things got a little bit crazy for everybody. Okay, and in these cores, we were finding just the kind of things we were expecting and hoping for. So this is an example of some of the sediment that we were pulling out. You can see all sorts of little gastropod shells in there. You can also see both aquatic and terrestrial plant macrofossils in there, which is important for us because for reasons of uptake of carbon, we like to use terrestrial plants for radiocarbon dating rather than aquatic plants. So it's good to be able to identify them and really good to be able to find the terrestrial species in there. More photos. This was the spot at University Bay. Here with this angle, you can see the UW Hospital in the background. And because we were collecting from very, very specific locations where we understood what should be going on, and we actually got it right with what should be going on, we found a very consistent set of sediments at all the cores. And so there were really only two variations, and there are only really minor variations of materials that we found. And the only difference is what was found at the base of the core. So in all the cores we found, very, very consistently, we found right over 2 meters of modern peat. Right below that, we found a material that we call marl, which is sediment that's deposited right at the edge of a lake. So we're getting that really shallow lake setting. And then we've got finely laminated lake sediment down lower below that. So just the kind of sequence that we'd expect. The only difference between the two types of cores that we got is that some of them got down to coarse material at the bottom that we interpreted as glacial sediment. So we got all the way to the bottom of the lake. Some of them, like in Cherokee Marsh, this is in meters, so we went down 15 meters or a little bit over 50 feet and didn't come within any indication that we were getting close to the bottom of it, and that was getting to the extent of our coring abilities. Within the peat, obviously peat is a datable material. We were looking to date some of the very bottom peat deposits. Within the marl, there were plenty of each of these little horizontal pattern lines represent sort of discrete layers of organic material that we were finding. So we were able to pick a centimeter or two layer to date. And then even down in the deeper lake sediment, we were finding occasional layers of plant material that we were able to date based on what we were interested in. So in many of the cores, we looked for the oldest dates, and best if we found them in cores that we had the glacial sediment, so we really knew we were right at the bottom of the lake deposit. And then we were also looking to date right at the transition from this marl, this shallow marine sediment, into the peat. So telling us when lake level fell down and exposed these areas above water level. With these cores, to give you an idea of how much material was in there, the 9 cores we collected, we had over 65 animal and plant macrofossils that we were able to identify and sample separately. Like I said, we focused on the lowest and the highest, and we got ages of right around 18,200 years before present for the formation of the lake, and this was repeatable in numerous cores. And then right around 11,200 for the end of the lake. So that would be when the lake fell down to the modern 4-lake level. So we go back to this. This gives us some chronology for Glacial Lake Yahara. We've also got this Glacial Lake Scuppernong. So I'm going to talk about it for a few moments here. So here are the cores that we collected in the Glacial Lake Yahara Basin. Over in Jefferson County, the project was a little bit different in nature. It wasn't looking at a specific geologic process or event like I was doing with Glacial Lake Yahara. This was my colleagues Elmo and Libby that were creating a geologic map of Jefferson County. So they weren't necessarily looking at Glacial Lake Scuppernong in and of itself, but they really had no choice but to look at it because they were looking at the county as a whole. So we found datable radiocarbon material in all 9 of our cores in Glacial Lake Yahara. In Glacial Lake Scuppernong, they only found 2, one way up here on the Dodge County line and one down here farther south, but that doesn't mean they didn't try or they weren't doing a lot of coring as part of it. They actually collected 49 additional cores to confirm the kinds of sediment that they were seeing in the county as they were creating their geologic map. And what they found was actually a story that was quite a bit different from sort of Lee Clayton's original idea of this huge expansive lake that had all these drumlin islands in it. They found evidence of a lake that was a lot shallower, a lot more dynamic than had been previously thought. So on this left-hand image, this big sort of circular spot that stands up as a high, this is a delta that was coming out from the ice margin and depositing sand and gravel in a big fan into this lake. Over here on the right, we've got a couple of deeper basins that you can see by the flats, but these green arrows are pointing out really nicely developed beaches that are still evident on the landscape, even though the lake has been gone for thousands of years now. If we look at some of the other areas, so the streamlined hills on here, these are drumlins, these are glacial landforms that are exposed. But you can also see sort of the ribbony shape of moraines cutting across. This is the Lake Mills recessional moraine cutting across the landscape. And if we look in closely, we can actually see lots of evidence of water flowing in single directions. So rather than a big lake that was all connected, it gave indications of really small basins, like one here that was draining down to the south, and this one here that was draining off in this direction. This one here was actually draining back in the opposite direction. So rather than one huge lake, it seems like it was more of a patchwork quilt of a whole lot of little lakes that were actually connected and feeding one another, probably in a very, very complicated kind of pattern. So that gives you a little bit of insight into that glacial lake Scuppernong. And now I'll bring it all together with sort of a broader, more unified kind of look at the area. So we'll go back in time to as the ice was starting to retreat. So this was after the ice had retreated from the Johnstown moraine, from the maximum position, and it was already pulled back at this point to the phase here where Glacial Lake Middleton existed right against the ice phase. So that would have been the Milton phase. We move forward in time to the early Lake Mills phase. So this is the second set of recessional moraines. And now we can see that Glacial Lake Middleton has drained. Glacial Lake Yahara has formed. And you get the very first evolution of Glacial Lake Scuppernong off here to the east. The ages we have from this, as I said, it was 18,200 years before present for the formation of Glacial Lake Yahara. From one of the two cores that was collected, 17,900 years before present for the earliest formation of Glacial Lake Scuppernong. Sort of internally, these are consistent. They're exactly what we'd expect to see, that Glacial Lake Yahara formed a little bit before Glacial Lake Scuppernong as the ice pulled back. We also like the consistency of these ages with all that previous work that I've done. The previous work indicated that ice began retreating from the maximum position at about 18,500 years ago. So that fits in nicely, and it's really important to us because it's completely independent data sets. These were collected from lake deposits at the Devil's Lake area. This is right in the Madison area. This is over in Jefferson County. So we've got three different areas, basically three different data collections, and the data is completely consistent from one to the next to the next. If we have the ice pull back a little bit farther, Glacial Lake Yahara will stay pretty much in its configuration that we've seen all along, and that's because it's confined in that bedrock valley. Even though the valley is mostly buried by glacial sediment, it was still enough of a topographic impediment to keep the lake here pretty well constrained. Over farther to the east, while there were other buried river systems in the bedrock of Jefferson County, the sediment cover was thick enough to completely obliterate the effect of it. And that's why you got this big sprawling lake that kind of went in every direction and flowed from little tiny basin to little tiny basin. So two neighboring lakes that were kind of behaving in radically different manners. Get a little bit farther retreat, same thing's going on. Glacial Lake Yahara stays in its configuration. Glacial Lake Scuppernong is just kind of sprawling all over the place in all sorts of different shapes. And then eventually ice retreated out of the region, and for some time afterwards, the lakes continued to exist, Yahara and Scuppernong. What controlled the demise of them was the Rock River. So the Rock River is where both of them drain off to the south, and as it cuts through the Johnstown Moraine, that was what controlled the elevation of the water in these lakes. And over time, as these lakes continued to flush water down that system, it cut that gorge deeper and deeper and deeper until it got to the point that both of these lakes drained out. And as I said earlier, the radiocarbon dates we have indicate that Glacial Lake Yahara dropped down to the modern Four Lakes right around 11,200 years before present. And over in Glacial Lake Scuppernong, some of those small basins, based on the radiocarbon dates from those couple of cores, indicates that there were still some open water lakes at about 9,100, so a good bit afterwards. But all of them had transitioned over to wetlands by about 6,800 years before present. And with that, I'd like to take a moment to thank some of the management organizations that gave us permission to get onto the land. Thank the Wisconsin Geological Survey, who supported me through the years with my research, and also State Map, which is a federal funding agency that funds a lot of the geologic mapping and research that we do. So thank you all for your time, and I'll be happy to take some questions.